All right, today in Algebra 2, we're going to look at section 6.2, the exponential models. We're going to focus on compounding interest today. Okay, so our 6.2 essential question, how can you develop exponential models to represent and interpret situations? After today's lesson, you should be able to write exponential models in different ways to solve problems. So first, we're going to look at rewriting an exponential function to identify a rate. So the problem says in 2015, the population of a small town was 8,000. The population is increasing at a rate of 2.5% per year. Rewrite an exponential growth function to find the monthly growth rate. So let's just recall from yesterday, we know that an exponential function looks like y equals a times b to the x power. We know that a is the initial population. B is the growth rate. X is going to be the time in years since, in this problem, 2015. So we would say Y is equal to 8,000. My growth rate, okay, so it's 2.5%. So as a decimal, that's 0.025. But since it's growth, we have to add 1 to that. So 1.025 and then to the x power. So now it says rewrite that growth function to find the monthly growth rate. Okay, so monthly, our x is in years. Okay, there are 12 months in 1 year. So we need to change this, okay, to 1.025 to the 1/12 power. So we're going to say this is 8,000. 1.025 to the 1/12 power. All of that raised to the 12x, since 12 times x is going to give us months instead of years. So the monthly growth rate, so the 1.025 to the 1/12 power, we would end up with y is equal to 8,000 times 1.00206 to the 12x power. So the monthly growth rate is, change this back to the percent, so is 0.206% per month. Right. So now we're going to talk about compound interest. Okay? Some real life application here for you guys. When interest is paid monthly, the interest earned after the first month becomes part of the new principal for the second month, and so on. Interest is earned on interest already earned. This is called compound interest because it compounds. The compound interest formula is an exponential model. This is the formula for compounding interest. A equals P times 1 plus R divided by N, all of that to the NT power. A is the value of the account after T years. R is the interest rate as a decimal. Remember, we always change it to a decimal. N is the number of times it's compounded. P is the initial investment or initial principal. That's how much you put in to start out with. T is your time in years. And so then we're just going to make sure that we know what these words mean. Some of the more common ways that it will be compounded annually. So annually means once a year. Semi-annually means twice a year. Monthly means 12 times a year. Quarterly, okay, think money. There are 4 quarters in a dollar. There are 4 quarters in a year. And then daily, 365 times. So let's work some problems doing that. It says Kale invests $5,000 in an account that pays 4% annual interest. How much will be in the account after T years if the interest is compounded annually, semi-annually, quarterly, or monthly? So our P, our initial investment, is the $5,000. Our rate as a decimal, so 4%, change it to decimal, is 0.04. Our time is going to be 3 years. So first, annually, n equals 1. So we would say A equals 5,000 times 1 plus 0.04 divided by 1 to the 3 to the first power. So that's 5,000 times 1.04 to the third power. When we work that out, and our units are going to be dollars, right? We would get $5,624.32. So in 1 year, or sorry, in 3 years, we've made $624.32 just in interest. Semi-annually, everything stays the same, except now our n is equal to 2. So we would say A is 5,000 times 1 plus 0.04 divided by 2 to the 3 times 2 power. So that's going to equal 5,000. So 0.04 divided by 2 is going to give us 0.02. So this is 1.02. 3 times 2 is 6, so to the 6th power. So do 1.02 to the 6th power, multiply that by 5,000, and we get $5,630.81. So if it's compounded semi-annually after 3 years, we would have $630.81 that we earned in interest. And go to the back to do the quarterly and the monthly. Again, everything stays the same except this time quarterly. Our n becomes 4. So we're going to have A equals 5,000 times 1 plus 0.04 divided by 4 to the 3 times 4 power. So we get 5,000 times, so 0.04 divided by 4 is 0.01. So add 1 to that, 1.01 to the 3 times 4 is 12. So we would plug in 1.01 to the 12th power, multiply that by 5,000, and we would end up with $5,634.13. So if they compound it quarterly, we made $634.13 in interest in 3 years. And then finally, monthly, our n is going to equal 12. So A is 5,000 times 1 plus 0.04 divided by 12 to the 3 times 12 power. So 0.04 divided by 12 is 0.003 repeating. What's very important here is that we don't want to round this until the very, very end. So this is going to be like 1.0033333, basically repeating all of that 3 times 12 to the 36th power. So do the 0.04 divided by 12, add 1 to that. Leaving that in our calculator, we will now raise that number to the 36th power and multiply by 5,000. And now we can round at the end, and we would get $5,636.36. So don't round until the end. So if they compound it monthly, after 3 years, we have earned $636.36 in interest. So then the question says, as the number of compounding periods increases, what happens to the amount in the account? Notice that it kept going up, right? So we started out once a year, we made $624.32. If they did twice a year, it jumped up to $630.81. Quarterly, so 4 times a year, it jumped up to $634.13. And every month, it jumped up to $636.36. So the amount in the account increases as the number of times it's compounded increases. So the more times your interest can be compounded, the more money you're going to earn, the better it is for you. So let's try some more of those. It says Owen invests $3,000 in an account that earns 3% annual interest, compounded monthly. What is the value of the account after 10 years? So let's identify our P, our initial investment, is $3,000. Our rate is going to be 0.03 as a decimal. compounded monthly, N is 12. And so on this first one, 10 years, T is 10. So A is equal to 3,000 times 1 plus 0.03 divided by 12. All of that to the 10 times 12. So 3,000. So do 0.03 divided by 12 and add 1 to that, and we get 1.0025. 10 times 12 is 120, so raise that to the 120th power. Multiply by 3,000, and after 10 years, Owen now has $4,048.06. So in 10 years, he made $1,048.06 in interest. Part B, what is the value of the account after 100 years? So all that we're going to do is change the T to 100. So this is going to still be 3,000 times 1.0025, because we did change how many times it's compounded, to the 12 times 100. So that's basically to the 1200th power, right? So 1.0025 to the 1200th power times 3,000. So after 100 years, Owen would have $60,031.45. That would be nice to leave to somebody, right? So now let's talk about understanding continuously compounding interest. So in order to do this, we're going to consider an investment of $1. So that's our initial principal. Account that pays 100% annual interest rate for 1 year. We're going to find the value of the account for the number of compounding periods in the table. Okay. So again, this is going to be our formula we use. 1 plus 1 divided by n, all of that to the nth power, right? Because what we're multiplying it by at the end, our initial investment was 1, so we don't have to worry about that. So number of periods n, 1. So if we do 1 plus 1 divided by 1 to the first power, we get 1 plus 1, 2 to the first power, which is 2. Now we're going to do 10. So 1 plus 1/10 to the 10th power. That equals 1.1 raised to the 10th power. When you plug that in your calculator, you get 2.59374246 to 100. So 1 plus 1 over 100 to the 100th power. So that's 1.01 to the 100th power, which is 2.7048133829. 1,000, right? So 1 divided by 1,000 is 0.001. So this is 1.001 to the 1,000th power. When we do that, we get 2.716933932. 10,000. So 1 divided by, 1 divided by 10,000, we're going to end up with 1.0001 to the 10,000 power. That turns out to be 2.718145927 to the 10,000ths. So this is going to be 1.00001 to the 10,000th power. That is going to equal 2.718268823. So it says, notice that as n continues to increase, so the bigger our n, the value of the account remains very close to what numbers? Okay, so here we have 2.7, 2.716, 2.718, 2.718. Okay, so it gets very close to the number 2.718. That number happens to be very special. This special number, 2.718, is called the natural base. The natural base, okay, E, so that is how we name it, is defined as the value that the expression 1 plus 1 divided by x raised to the x power approaches as x approaches infinity. The number E is an irrational number. So if you typed in E in your calculator, it's really 2.7182818282459 ... All of our calculators will have an E button. So the number E is the base that we use in the continuously compounding interest formula. So this means continuously compounded. It's compounded every second, every millisecond of every day. Okay? So this is the formula that we use for continuously compounding. A equals P times E to the RT power. Okay, so again, A is the value of the account after T years. P, is still the initial investment or the initial principal, what you started out with. E, that is the natural base. And again, you will use that button on the calculator. A is still your interest rate as a decimal. Okay. So now we're going to practice using that button on our calculator and finding continuously compound interest. So it says Callie invests $12,600 in an account that earns 3.2% annual interest compounded continuously. What is the value of the account after 12 years? Round your answer to the nearest dollar. Right? So let's just plug into the formula. So A, that's what we're looking for, equals P. How much did we start out with? 12,600. Always to E to the RT power. So our rate as a decimal, 0.032 times 12. So really we have 12,600 times E. If you multiply 0.032 times 12, you get 0.384. So in our calculator, we could do the E button, raise that to the 0.384, and multiply by 12,600, and you will find that you get $18,499. It says round to the nearest dollar. Okay, so after 12 years, okay, we went from $12,600 to $18,499. All right, the next one says Hunter invests $125,000 in an account that earns 4.75% annual interest compounded continuously. What is the value of the account after 15 years? Okay, so again, A equals, what did we start out with? 125,000. E to the, our rate is 0.0475 times our time, 15. So this is really 125,000. And E, if you multiply 0.0475 times 15, you get 0.7125. Our calculator, and we get $254,885.32. Pretty nice investment there, isn't that? So now part B, same thing, only now what would be in the account after 30 years? So A equals 125,000. E to the 0.0475 times 30. So this is 125,000. E, if I do 0.0475 times 30, I get 1.425. Put all of that in our calculator, and we end up with $519,732.23. Again, very nice investment. So now we're going to look at how do we use 2 points to find an exponential model. So this first one, it says that Taylor knew that the number of emails she sent was growing exponentially. She generated a record of the number of emails she sent each year since the year 2009. What is an exponential model that describes the data? Again, we know y equals a b to the x. That's what we're trying to get. We know that y, that's the number of emails. That's the end result, so the number of emails. And we're going to go ahead and say in thousands, so we don't have to put huge numbers in our equation. X is going to be the number of years since the beginning. So since when she first started was 2009. So we look at the data over here. They show me in 2016, she sent 1,400 emails. In 2015, 1,000 emails. We need to find the growth factor. We use consecutive years. So we're looking at between 2 consecutive years. So in 2016, she sent 1,400, but we're doing 1,000 in thousands, so I can just say 14 over 2015, 1,000, so that would just be my 10. So our growth factor is the 1.4. Remember, this is our B. Okay. So now we need to find out what is A going to equal. So I can plug in everything that I know to find A. So we know that in 2016 she sent 1,400. So we're going to say 14 equals A. That's what we're looking for. Times B, our growth factor, 1.4. And then to how many years? So how many years was it from 2009 to 2016? So 2016 minus 2009 is our X value. So X is 7 to the 7th power. So I want to solve this equation. So do 1.4 to the 7th power and then divide 14 by that. When we do that, we find that A is approximately 1.33. Therefore, the model equation that we could say for Miss Taylor would be y equals 1.33 times 1.4 to the x power. So she could use that model to find out how many emails she sent in any year, right, past 2009. Okay, let's look at one more of those. So on the last page, it says Isaac determined that the value of an area of land over a period of several years since 1950. The land was worth $31,000 in 1954, $35,000 in 1955. Use the data to determine an exponential model that describes the value of the land. Again, first we need our growth factor between 2 consecutive years. So between 2 consecutive years, we've got 35,000 divided by 31,000. And that's going to equal 1.129. There's our growth factor. So now if I want to find my A, so I'm going to look at 35,000 is equal to A times my growth factor, 1.129. Now how many years? So we used 1955. We started out in 1950, so 1955 minus 1950 is 5 years. So if we solve that, we get that A is approximately 19,081. So then we could say that our model, y equals 19.081 times 1.129 to the x power. And that would give us a nice model to determine how much the land is going to be worth in any year since 1950. And that's where we're going to stop for today. Tomorrow we will pull out our graphing calculators and use those to find exponential regression models. Let our calculator do the work for us. You can find your homework assignment in today's Canvas announcement.